Here we are going to see how we can use the Smith chart to find out the VSWR, VSWR and the location of Vmax and Vmin in the transmission line using the Smith chart. Let's start with what is meant by VSWR or VSWR. So if you have the system like this, the waves from the source will be transmitting through the transmission line and will be reaching on the load impedance. Depending upon the impedance mismatch between the load and the transmission line, some part of the wave will be reflected back and the incident wave and the reflected wave will interact and will result in the standing wave. So this is an animation showing that interaction. So here the blue line shows the incident wave and the orange line shows the reflected wave, and the green line is due to the interaction of incident and reflected wave. So here you can see that based on the interaction between the incident wave and reflected wave, the amplitude of the standing wave is getting maximum and then it is going to reduce to minimum value. So this is just some screenshot from this animation to show what is meant by Vmax and Vmin. So if the incident and the reflected wave has the same phase, it can result in maximum value of the standing wave. And if the incident, that is this blue, and the reflected wave has the opposing phase, it can cause the minimum amplitude. So this is how the Vmax and Vmin are occurring. So the VSWR is the ratio of maximum to minimum voltage on a transmission line. So it is actually measured throughout the transmission line to find out what is the V minimum and V maximum through the transmission line. So in earlier days, it was like we have to measure through this transmission line to find out what is V max and V minimum. So the Smith chart was a very useful tool to find out where this Vmax occur or where the V minimum occur. So this is the definition of VSWR. So it is the ratio of max to V minimum, and Vmax is defined as V incident plus V reflected. It occurs when both incident and reflected have the same phase. V minimum occurs when both the waves having the opposing phase. So let's see how we can relate that to the Smith chart. So when we studied about the Smith chart, we know that this is the position of the short. Here comes the short and here comes the open. So in the short position, the reflection coefficient gamma is given by 1 angle 180. This means that when the load is short, the reflected wave will be out of phase. So when the reflected wave is out of phase, that is when the incident and the reflected waves are out of phase, it can cause V minimum. So that means that at this short position, as the incident and reflected wave has 180°, this position becomes V minimum, and at the open position, as the you can see the phase is 0°. This means that incident and the reflected wave are having the same phase. So this is the condition. So here we can expect V maximum. So this position will be the V maximum position. That means that when we are considering the Smith chart, we can consider this is the short is the position of the V minimum and the open is position of the V maximum. So in this transmission line, if we are considering the transmission line, this position we have to consider as V max and this position we have to consider as V minimum. So let's see why it is important to understand this concept. So we know that the standing waves are occurring due to the interaction between incident wave and reflected wave. So these standing waves are happening in this transmission line. So let's draw. So these transmission lines are happening inside this transmission line. And we have to find where is the position of the V maximum and where is the position of V minimum happening. So in that case, we have to consider the length from the load to the source. So lmax correspond to position of the Vmax from ZL, and lminimum corresponds to position of Vminimum from ZL. So for this purpose, we can use wavelength towards generator because we have to consider the length from load towards the source to find out the position of the V maximum and V minimum. So we can consider wavelength towards generator. Here you can see wavelength towards generator position. So you can use this one to find out the position of the Vmax and Vminimum. And let's see how the VSWR is defined on the Smith chart. So if you draw the constant VSWR circle, because we know that the gamma, the reflection coefficient, is defined by this expression. So we can easily draw the reflection coefficient using this expression, and VSWR is related to the gamma by this expression. So we can easily draw the constant VSWR circle on the Smith chart. So if you draw the constant VSWR circle like this, here you can see that I'm just zooming out in. So here you can see that this is the constant VSWR circle corresponding to VSWR 1.5. Here you can see that it is crossing on the pure resistance line. So this is the pure resistance line. It is crossing the pure resistance line at 1.4. So this is 1.4. This line is 1.5 and this line is 1.6. So if the VSWR is 1.5, it is having the same value on the pure resistance axis. Similarly, if the VSWR is 2, it will be having the same value on the pure resistance axis. That means that if you want to find the VSWR of a load, you have to just draw the circle and can find the intersection point to find the VSWR. So this is one of the property of VSWR and the pure resistance line. So the intersection point of the VSWR and the pure resistance line will actually indicate the VSWR value. So let's consider a real type scenario in order to find out what is the VSWR and what is the position of the lmin and lmaximum. So here is the question: for a lossless transmission line, the characteristic impedance is 50 ohm. It is terminated with a load impedance of 50 plus 50J. What is VSWR, L minimum and L maximum? So if you have to deal with the Smith chart, the first thing you have to do is normalize this thing. So you have, for normalization, always divide this by the characteristic impedance. So it will be 50 plus 50J by 50. So it will give you this value. So the next step is just mark this point on the Smith chart. So we have marked this point on the Smith chart. So this is the resistance value and it is 1J plus 1J. It means that it is an inductor value. So this is the resistance circle corresponding to 1 and this is the inductance circle corresponding to plus 1. So this point give you the value. So our next aim is to find the VSWR. So one thing you can do is you can draw a circle with the center at this point and radius like this and find out the intersecting point on the pure resistance. So this is what I have done. So I make this point as the center and the draw a circle like this. So here you can see that the intersecting point on the pure resistance. So this is 2 point. So this is 2. This one is the 2, 2.2, 2.4, 2.65. So this is the value. This value gives the VSWR. So this value, the intersection point, gives the value VSWR. So this is one method to find the VSWR. Another method is just draw a line from this point to that point and measure this distance. So if you measure this distance on the below portion, you can see SWR. Here you can see like, okay, so I will zoom in. So here you can see SWR. So draw the same distance on this line. So if you draw the same distance on this line, you can see the length of the line on this SWR. So that is 2.65. This will also give you the VSWR value. So the below line shows the VSWR value in dBs. So this can also be used to find out the VSWR in dB value. So if you have to find out the VSWR, you can either draw the circle and find the intersecting point on the pure resistance line, or just measure this distance and draw that same distance here. So that will also give you the VSWR value. So this is how you have find out the VSWR. So you get the VSWR as 2.65. So our next purpose is to identify from at which position on the transmission line Vmax and Vmin occur. So for that, what you have to do is first you have to find out the length of the load in wavelength. So for that, what you can do is you can extend the line through this point. So this is our point representing 1 plus 1j. So just extend this line from the matched position through that point and extend to outer of the Smith chart. So to find out the length of the load impedance, what we have to use is we have to use wavelength towards generator. So you have to actually use this outer circle, wavelength towards generator. So that is outer circle. So this is rotating like this. So from generator to the source, you have to consider the outer circle. So I am going to consider that outer circle. So it will start from 0, 0.04, something like that. And you can see 0.13, 0.14, 0.15, 0.162. So this is the length of the load here. So for 1 plus 1j, the length of the load is 0.162. Our next step is to identify lmax, so where this Vmax occurs on this transmission line. So previously we have seen that this is the open position and here comes the Vmax. So we have to just identify this distance of separation between this point and our Vmax. So we know the length up to this point, which is 0.162. So we know that the maximum will occur at 0.25. So we have to just find out the remaining length. So for that we have to just extend from 0.162 to this Vmax point. So here we can see that the value is here 0.0, 0.24, 0.25. So if you have to extend from 0.162 to 0.25, you can do is just uh, calculate the value, or just you can do 0.25 minus 0.162 lambda, because this 0.25 correspond to this value. Means if you are extending wavelength towards generator, here it comes 0, here it comes 0.25. So the Vmax corresponds to 0.25 lambda. So 0.25 lambda minus 0.162. That will give you the position of the Lmax. So you get the position of Lmax as 0.088 lambda. And next step is you have to find the L minimum. So we know that V minimum occurs at this point, and which is corresponding to, you can see here 0.48, 0.49, 0.5 lambda. So this position corresponds to 0.5 lambda. So you have to extend from 0.162 to 0.5 lambda. So you have to find this distance. That is distance from this load to the V minimum point. So that will give you the length of the transmission line where V minimum occurs. So for that, what you can do is you can just subtract 0.5 lambda minus 0.162 lambda. So this is the length which will give you the position of the L minimum. So now we have identified the position of the V minimum, position of the V maximum, and also the VSWR. So this is how you can utilize the Smith chart. So this is just the cross verification using the equation. Here you can see that the reflection coefficient can be given by this expression. So we have this is our load. By substituting, you will get the reflection coefficient as this value, and when you calculate VSWR, it is giving the value of 2.62, which is same as we have calculated from the Smith chart. So using the Smith chart, we don't have to use these type of complex calculation. We have to just make the point on the Smith chart, just measure it, and we will be very easily able to identify the VSWR from the Smith chart. And okay, let's see another question where my load is 50 minus 50J. So previously I have considered the load of 50 plus 50J. So now I'm going to consider a capacitive load 50 minus 50J. So the first step, if we have to do anything on the Smith chart, is find the normalized impedance. So that is divide this by the characteristic impedance. So I have calculated the load impedance, and next thing is mark out that point. So this is 1 minus 1J. So this is the constant resistance circle corresponding to 1, and this is minus 1. As it is the capacitance, that is minus 1J, it will be below this part. So minus 1, so here it will comes. So this is the intersecting point. So just mark that point. If you want to find the VSWR, what you can do is just measure this distance and plot the same distance on the SWR curve. So that is what I have done. So I just plotted it, and when I measured the same on the SWR, it is 2.65. So for 50 plus 50J and 50 minus 50J, so if it is the inductive or the capacitive impedance, you can see that the VSWR value is same. So my next purpose is to identify the Lmin and Lmaximum. So here to find the Lmin and Lmaximum, what you can do is just extend this line through this point, and here you can see that what is the intersection point on the outer circle. So it is around 0.33, 332, 334, 336, 338. So 0.338 is the value corresponding to the load. So we know that we have to consider wavelength towards the generator. So the rotation is like this. So if you rotate like this, you can see that this is my load impedance, and if I rotate through this line, you can see that V minimum comes before V maximum. So in this transmission line, when the reflection occurs from 50 minus 50J load, the V minimum will be occurring first, and then comes the V maximum. So to find V minimum, what I can do is, so we know that V minimum occurs at 0.5 lambda. So the V minimum occurs at this distance. So to get that distance, what I can do is I can just subtract 0.338 from 0.5 lambda. So that will give me the position of the V minimum. So this is the value of V minimum, and V maximum will be occurring at this position. So if I have to find the V maximum position, I have to extend my load through this distance. So I actually calculated the distance from here to here as 0.162, and we know that from here to here it is 0.25 lambda, because you can see it will start from 0, and when you extend to this point here, you can see it is 0.25 0.25 lambda. So to calculate the overall distance, what you can do is you can add 0.162 plus 0.25 lambda. That will give you the position of the Vmax on the transmission line. So this is how we are calculating VSWR and the position of the Vmin and Vmaximum. So in earlier days, for calculating VSWR, it means we have to make the measurements on the transmission line. So by using the Smith chart, it was very easy to find out where this Vmaximum and Vminimum occur. So I hope you get idea about the importance of Smith chart in VSWR calculations. Thank you.